going to do is work through several case studies. So you'll see it sort of get more and more applied. I'll start with doing a little more of alloy theory and cluster expansions, which sort of is really a follow-up on the Monte Carlo work we did, and you'll see how that fits in with coarse-graining. So essentially the part we didn't get to when I finished. And then I'll do a variety of things on Tuesday. One of them is kind of neat, is accelerated molecular dynamics techniques, which is sort of a specialty topic, but it gives you an idea of where people kind of, are trying to push the boundaries. And then on Thursday, we'll actually have a guest lecture. We'll have Chris Wolverton from Ford Motor Company lecture. It's kind of cool. He actually lectures from Ford, so you're going to see him project on the screen. He does that every year, and people usually find that a really good lecture. He essentially talks about how they use modeling in general, but in particular first principles methodology at Ford Motor Company. He has a few really cool stories. He won't tell you how much money they saved the company, but it's actually in the tens of millions of dollars, so that's why they're still there. He won't tell you that, but I can tell you that before his talk. So that's on Thursday, and then we go into the last week, and I think we have only one more lecture left there. So one of the things I wanted to do today is be a little more systematic about some of the models we've introduced. Like for your lab, we introduced this lattice model, for example, to model hydrogen absorption on palladium. And several people had questions, how do you know that this is a good model? Those lattice models are actually occur all the time in solid state structure equilibration thermodynamics. And I'll sort of go through them a little more systematic today, and then in the end, towards the end, prove you that they actually are a very accurate representation of the thermodynamics of real systems. So let me sort of show you again where they will tend to show up. I introduced the lattice model to you simply as a magnetic spin model. Remember, that's how we started. You model a magnet and you have up and down spins. But as soon as you realize that those spins are really just general occupation variables, sort of they tell you the result of a binary outcome, you can also use them to represent a whole lot of other things. For example, if you look at superstructures in the copper-gold system, copper is FCC, gold is FCC, all the structures in between are on FCC lattice. So if you really want to know how they look, the question is, how do you distribute copper and gold on an FCC lattice? So really all you need to know is on every lattice site, is there a copper there or is there a gold? So again, that's a binary outcome, so you can represent that with spin variables. So essentially, the energetics and thermodynamics of this will be represented by a spin model, okay? Also by a lattice model. It doesn't necessarily have to be atoms. It can be atoms and vacancies. This is an example I'll come back to later. This is lithium cobalt oxide. The purple things up there are lithium. Red is oxygen, and the green is cobalt. When you can actually extract lithium from these materials, and so start removing some of the lithiums. And so essentially what you have then is a distribution problem of lithiums and vacancies on a given set of sites. In this case, those planes that you're looking head on are actually triangular lattices. Okay. And I'll come back to that as well. So here the spin variable would indicate whether a site is occupied by a lithium or not. You can do surfaces. That's, lattice models are classics for surfaces. Here's a typical 1-1-1 surface with stuff absorbed on it. So if you look at an FCC metal like platinum and you look on the 1-1-1 surface, the absorption sites of the same symmetry, for example, the hollows, which I've kind of indicated here. So the hollows form a triangular lattice. Okay? And so if you look at absorption, again, all you need to know is there something at the absorption site or not? So again, you would use a binary variable. So what I first want to show you is that an Ising-like model, or a lattice Hamiltonian, as you've seen before, is actually a very natural way of writing the energy. And actually, I extend that later to any property of configuration. So So I'm going to do that a little more formally than we've done before. Essentially, if you want to study all these models that are lattice models, you need some Hamiltonian for them. And so I'm going to use this sigma between these squiggly brackets as a variable to indicate the configuration on the whole lattice. So the variable sigma is essentially a combination of sigma 1, sigma 2, sigma 3. So you can think of it as a vector in the configurational space of all the occupation variables. So what you need is a practical way of writing that configurational Hamiltonian. And the way you write out almost any practical Hamiltonian or any practical energy function that you want as accurate as possible is that you write it as some expansion in a suitable basis set of functions. Okay? Think of how you expand wave functions in plane waves, how you sometimes expand it in sines or cosine. The typical basis that's used here is what's called cluster functions. A cluster function, which I'm going to label by phi alpha, is essentially the spin product of all the sides of that cluster alpha. So if I make a pair cluster, let's say this one, I and j, the cluster function phi alpha then is sigma I times sigma j. But I can make many other ones. I could make sort of a four-body one. They don't even have to be connected. And so for the red, phi alpha would be, let's call it I, j, k, l, would be sigma I, sigma j, sigma k, sigma l. Okay. I think the computer gets more tired as well as we proceed. Okay. The first thing, so when you expand in a basis, you want to make sure that the basis is complete to describe your full space. And then sometimes it's useful that your basis set is orthogonal, although that's not really necessary, but it can be practical. It's easy to see here that it's complete. I mean, if you have n lattice sites, what's the size of the space? What's the size of the configurational space? Well, it's 2 to the n. On each lattice point, you can put two things essentially. So the number of combinations is 2 to the n. Well, how many basis functions are there? Well, if you think of what's a choice of basis function, it's essentially picking a combination of sites. So that's also 2 to the n. There are 2 to the n combinations of sites because it's also a binary problem. For every site, you include it or you don't include it in the basis function. So there are 2 to the n basis functions. I'm going to show you in a second that they're orthogonal. So the basis set is complete in a very trivial sense. There are as many basis functions as states. Okay? So you may ask yourself, what have you won? We're actually going to expand things in this basis set, but there's as many basis functions as state. Well, the hope is that we can formulate these basis functions so that whatever quantity we expand is more rapidly convergent. So let me prove you that the basis set is orthogonal if you take a suitable scalar product. The way I'm going to define the scalar product between, say, any two functions of configuration, which I'll call f sigma and g sigma, okay, I'm going to define the scalar product simply as the sum over the configuration space properly normalized. Okay? So, this is equivalent to if you're working in a continuous space, defining your scalar product as the integral of the product of the two functions over the configuration space. And you might be more familiar. Because we have a discrete configuration space, that integral is essentially a sum over all the possible configurations. Let me prove you that the functions are orthogonal. First, you can note that for any basis function, if you sum its value over the space, it gives you 0. And you can easily see that, let's say that function will look something like sigma I, sigma j, sigma k, maybe with more terms. Essentially, these terms will alternate as having plus and minus 1, and so they will sum to 1. Using that, you can easily prove that the functions are orthogonal. So if you dot the two basis functions into each other. So you're essentially summing their product. Okay. So let's say we have a cluster alpha and a cluster beta. You know, maybe this is the cluster alpha, and maybe this is the cluster beta. Okay, so they have a partial overlap. So you can write the product of alpha and beta then as first as the product of the spins that are in both alpha and beta. And for those of you get sigma I squared. And then the spins that are only in alpha and the spins that are only in beta. Of course, sigma I squared is always 1. Okay, because sigma is plus or minus 1, your occupation variable in a spin model. So essentially this goes away. Okay. And this is simply a function. You could write this as the basis function of alpha plus beta minus alpha intersection beta. Okay? You're essentially here multiplying all the spins that are only in alpha or only in beta. Okay, but not in both. So that's trivially 0. So the only time that this product is not 0 is when this part doesn't exist. That means when all the spins are in both alpha and beta. Okay? So this product is equal to the Kronecker delta. It's actually not this product, I'm sorry. It's this product summed over all configurations. So I should correct this. It's 1 over 2 to the end. Sum sigma. And then that should go in front of here. Okay. So the basis set is orthogonal. Okay. So we have a very practical expansion now. We have a complete and orthogonal expansion. So one of the first things we're going to do is expand the energy in this basis set, because the energy is a quantity we'll need in things like Monte Carlo simulation. But you should right away see that this is much more powerful. Huh? You can expand any property of configuration in this basis set. They will have, may have different rates of conversions, but essentially this is a basis set in which you can expand anything that depends on how you arrange the atoms on a lattice. So people have done things like expand the band gap of materials. Okay? And if that converges fast, you have a model that you can rapidly search then. People have expanded things like the vibrational entropy in it. People have expanded things like, I even tried to expand things like conductivity and so, which goes not as well. But essentially anything that becomes a property of the arrangement of atoms on that lattice, so in that substitutional space, can be expanded. For now, I'm going to stick to the energy. So if we expand the energy as a function of configuration, so we get an expansion over all the possible clusters alpha, the basis function, and then the expansion coefficient, which we'll call V alpha. And it's, of course, the expansion coefficient that's going to contain all the energetic information. And I'll show you in a second how it's defined. But first, I want to write out what this cluster expansion, as it's called, looks like. I mean, if you pull out what these cluster functions are, you'll essentially get something that looks like this. There'll be an empty cluster function. So that's this term. When alpha is just a point, you'll have this term. So this is almost like point site energies or chemical potential likes. If alphas are pairs, you'll get the standard pair term that we see in lattice models. But this keeps on going. Huh? You'll have triplet terms, quadruplet terms, and so on. So essentially, the cluster expansion is the same as what's called a generalized Ising model or Ising model. Okay? So where you go away from relying only on two-body terms to sort of higher body terms as well. And what it essentially is a generalization of that approach. I'm sorry, I'm going back and forth. I'm interchanging and using E and H for the Hamiltonian, E for the energy. And that's one of the reasons is that I cut and paste equations from various PowerPoint slides and wasn't quite able to modify them due to the great Microsoft software. Okay. But I think what's the really nice thing is that this formal expansion will allow you to define exactly what these V's are. Because you may have asked yourself, you know, when you were doing in the lab, and are probably still doing, the hydrogen on palladium, what those interactions actually are. Are they sort of physical potentials between the hydrogen or not? You'll see in a second that they're not, that they're much more complex than that. Okay. So, you know, whenever you write an expansion in orthogonal basis functions, how do you get the expansion coefficient? Well, the expansion coefficient is essentially the projection of your function onto the corresponding basis function. And that's what you'll see here, and you'll get something really interesting come out. So the way to know how a V alpha is defined, you can essentially take the scalar product of this expression on both sides with phi beta. So you multiply with phi beta and then sum over all configurations. Okay? So you're essentially taking the scalar product here. Huh? Phi beta, phi beta. On this end, we know that this is the Kronecker delta, so this is V beta. Okay? So we've projected out V beta out of this expansion, and now we have to work out essentially what this is to know exactly what V beta means. And you'll see this is the projection of the energy onto the basis function phi beta. But it's interesting when you work that out, what it physically looks like. So that's what I'm going to do here. So I've written out the scalar product here. Okay. What I'm going to do is I'm going to set, this is the sum over all possible configurations of the lattice. Since I have a basis function phi beta here, I'm going to separate that into a sum over the spins, the configurations on the spins that belong to beta. So let's say this is beta, you know, some triplet. So I'm going to sum over those spins and then separate that and sum over all the other spins on the rest of the lattice. So I've written that here as a sum over all the i's. This should be, sorry, this should be sigma I, that are in beta. And summing over all the configurations, you get that by just making all the sigma i's plus or minus 1. Okay? And then summing over the configuration space minus what lives on beta. And this is a bit shorthand notation. It's a little hard to write formally what you're actually doing here. But those of you who are familiar with quantum mechanics and so may recognize this as a reduced trace. You're essentially tracing over all of the configuration space except what lives on beta. Okay? Okay, so what I want to do is work out the example for a pair interaction, since the math is about just the right level to do in class. A three-body gets a little harder. So we're going to work this out when beta consists of sites I and j. So it's a pair interaction. So you see that in this first term, I'm going to get 4 terms. Okay, because I have 2 sites. I can do A or B. Let's say, let me call, you know, plus 1 is A, say, and minus 1 is B. So if I do the term, let's say I do the term I equals plus 1, j equals plus 1. Okay? So the basis function is going to be 1. Okay? Because I have plus 1 times plus 1. And then what is this really? Think about this. So when I and j are plus 1, that means I essentially decorate this cluster of sites I and j with an A atom and an A atom. So it's an AA pair. But what is this term? Essentially, I'm summing over all the configurations outside of this cluster. Okay? All the spins. So this is essentially the average energy of the AA of the configuration with AA pairs at ij. Because look at what I'm summing over. So I'm summing over the energy of all the possible configurations, but it's configurations that have a fixed beta occupancy, because I'm not summing over beta. So this first term is essentially what I'll call EAA averaged. So do you see what it is? It's, I put A at J, A at I, A at J, and then I essentially trace over the remaining configuration space. So I put all possible configurations on the rest of the system and calculate that average energy. Okay? So you can do that for the other terms. So I'll write out explicitly now Vij, because beta is a cluster consisting of I and J. We're going to find is n beta is the number of sites in beta, so we get 1 over 4, because the number of sites is 2. So the first term I got was EAA. Okay. If I do I equals -1 and J equals -1, I'll get, again, a plus for phi beta, so I get plus EBB. And then if I do I and J a different spin, so +1 and -1, I'm going to get minus EAB minus EBA. Okay, does everybody roughly see where that comes from? So I essentially explicitly evaluate the 4 terms in that sum. Okay, and every time I essentially get the average energy of that configuration. If your system is symmetric, if I and J are equivalent, then these are the same. Okay, if you have translational symmetry between I and J, so then you'll get something like -2 EAB. And those of you who've seen like regular solution thermodynamics may recognize this very much as a sort of effective prefactor in the enthalpy of mixing. You'll get something like the AA interaction plus the BB interaction minus 2 times the AB interaction. But just sort of pointing that out. But it's sort of interesting. This is the formal definition of the expansion coefficients. First of all, notice that they are not potentials. They are energies. Okay? And they are energies of configurations. So, you know, this is not the potential between the AA atom at the A atom at I and the A atom at J. Okay? The reason is that the configuration around it modifies that interaction substantially. Okay? Typically what you'll find is that these V's are much, much smaller than direct interaction energies. And the reason is they contain an enormous amount of cancellation. If you think about it, this is AA energy, BB energy, and -2 times the AB energy. So they're often several orders of magnitude smaller than direct interactions, if such a thing were to exist. The other thing is that indirect effects can be included. Like if you truncate your lattice model at pair terms, okay, because it's an infinite expansion, at some point you'll have to truncate it, you are still including many body quantum mechanical effects, because the many body quantum mechanical effects enter in the calculation of the energy of these. Okay, so what you should understand is that the level of physics, or the level at which you truncate the cluster expansion, the lattice Hamiltonian, has no correspondence to the level of physics for your, say, your electron physics. Okay. Let me give you an example just to sort of think through what these things are. Let's say you had a model on a lattice where things just interacted with pair potentials. Okay, so a very simplistic energetic scheme. If the atoms don't relax away from the lattice points, okay, then you can really, then these energies can really be written as a pairwise sum. Okay, because then the total energy of a system is really the pairwise sum between all the pairs. And then what you're going to find is that essentially all of the pairwise sum cancels in this difference except the AA interaction, the BB interaction, and the AB interaction. So if you do just a pairwise energy expression, and you should try this once, it's sort of very pedagogical, and the atoms don't relax away from the lattice, okay, then you'll find exactly that these are pair energies, okay, pair potentials. Now, as soon as you let the atoms relax away from the lattice point, you know, like maybe the A1 is bigger than the B1, even in a pairwise energy Hamiltonian, these will not be the pair interactions, okay? Because you cannot remove from these energies, you cannot cancel the energetic effects between A and the rest of the material and B and the rest of the material, okay? So the really cool thing about these expansion coefficients is that they will include all that extra physics like relaxation away from the equilibrium lattice side, and I'll come back to that later. Come on. Shouldn't write so much. Class is over, no? Here we go. So, I'll go back and forth between writing the cluster expansion in terms of the phi alpha, so the basis functions, or being more explicit and writing the basis functions out as the products of spins right away. So all your physics of your system, all the energetics sits in those coefficients V, of course. So the question is, how do you get them? Well, there's a lot of different ways that people have tried to get them, and it depends a little bit on the problem. For simple Hamiltonians, you can often do really just calculate them directly by their definition, essentially as the projection of the energy onto that basis function. You can do that for pairwise Hamiltonians, even including force relaxation. So even when atoms don't sit on a lattice, you can do it by Fourier transforming, and that's in one of the references that I give you. But as soon as your physics is very multi-body, it becomes very hard to do it analytically. There are people who do it numerically very much according to the definition. So you literally, you take a system with, put an AA atom here, and then calculate a lot of different configurations around that. And so literally start to approximate those averages, EAA average, EBB average. The practical way that's people pretty much do it now most of the time, which is also the least elegant way, is that essentially you fit your whole expansion at once to a large number of energy calculations. So the first thing you have to do, of course, is to truncate your Hamiltonian, because this is an infinite expansion. Huh? You should really see this. This is a trivial expansion. You're expanding 2 to the n quantities in 2 to the n basis function. Okay, so it's only practical if you truncate it. But once you truncate, you have a finite set of coefficients to determine. So what you can do is literally calculate the Hamiltonian, or in this case the energy, for a lot of these configurations. Let's say there's 20 of these V's you have to determine. Then essentially, if you have the energy at 20 different configurations, you could, determine the interaction coefficients. Typically, people use very overdetermined sets. So, if you want 20 of these, you may do 50 of 50 energies and do a kind of these squares fitting, just to make the determination of interactions much more stable. But so that's essentially how it's done. You have an energy method. I sort of wrote that as a first principles method here. Could be any energy method. You calculate a lot of energies of different configurations, and then you fit the Hamiltonian, and you get the interactions out. It's really that simple. And once you have your lattice model Hamiltonian, you now know that it's fairly easy to equilibrate that. So you can get ground states out of that. You can do Monte Carlo simulation on it, just like you're doing in the lab, and then get phase diagrams, thermodynamic properties out. So essentially, you can get both the structures and all the thermodynamic information, and more important, as I'll show you in a second, all the information you can derive from that thermodynamic information, which is something people often forget. So what I was going to do is show you a few examples of kind of how this is used, and then in the end essentially come back to some of the theory of that. Here's one that shows how elegant it can be. This is what I'm going to show you is a calculation to try to get the solid part of the calcium oxide, magnesium oxide phase diagram. This is sort of perfect for a cluster expansion. Calcium oxide and magnesium oxide are both rock salt structures. So a rock salt is essentially an FCC lattice of oxygens, which I think are in this picture, the purple ones. And then the cations, either calcium or magnesium, sit in the octahedral sites, octahedral interstitials. And the octahedral interstitials of an FCC lattice also form an FCC lattice. So you can think of rock salts as two interpenetrating FCC lattices, one of cations, one of anions. So when you mix the two, you're essentially asking the question, at each interstitial, is there a calcium or a magnesium sitting there? So again, you have a perfect binary problem. It's a lattice model. But this already illustrates sort of a nice thing of this approach. In your whole lattice model, the oxygens won't appear. So the variables you use are only going to be defined on the cation lattice. So the cations are the smaller ones. So on this one, you'll have, sigma I is say +1, and on this one, you'll have sigma j equals -1. So you're essentially going to express the energy solely in terms of spin variables on the cation sites. And that makes sense. There's nothing unknown about the anion sites. They're always fully occupied. Okay? So the anions will show up when you calculate the energies of these configurations, of course. But there's really no need to expand the energy in their occupation variables because they're always there. They're always -1. So you see, we're going to end up with an effective Hamiltonian between the cations that includes the energetic intermediary of the anions without explicitly including them. So how do you do something like that? Well, you truncate your Hamiltonian number. It's always going to be the same procedure. You calculate the energy, a lot of different configurations. This is old work, so it wasn't fully quantum mechanical. There are two sets of points. So this is actually energy. I'm sorry, this is in electron volt per cation. The blue points are done with empirical potentials. Remember, we did that all the way in the beginning of class. These are essentially Buckingham potentials with electrostatics and shell models attached to them. And the open red circles is a self-consistent PIB, which is a really poor man's quantum mechanics. It's a sort of intermediate between Thomas Fermi theory and better quantum mechanics, but think of it as a poor man's quantum mechanics. And these are mixing energies, so they're referenced to 0 here and here. Okay, that's why they have that sort of parabolic shape, because you force them to 0 at 0 and 1. First of all, they're positive, so that means the two things don't want to mix. It is in accordance to the phase diagram. But you may notice something already that's kind of interesting. The quantum mechanical values actually tend to be lower than the potential ones. And this is very common. Typically, a better energy model will lower the energy of low symmetry states more than a bad energy model. And the reason is that usually a good energy model has more degrees of freedom. Okay? If you think of, your potential model has no electrons in it. There can be no electronic relaxation by definition in a model with empirical potentials because you don't have electrons. Okay? A quantum mechanical model has electrons in it. So you have more ways for the system to relax. And the lower the symmetry, the more a system can actually use those methods. If your system is fully constrained by symmetry, then there's barely any way the system can relax. Okay? So this is something you very typically see. If you have energy methods that are fitted to perfect bulk properties, so they're fitted in high symmetry environments, if you then use them on defect properties, the better the physics of the model, or the more degrees of freedom usually, the lower the defect energy will be. But anyway, so you'd use this, you know, you'd fit your Hamiltonian to it, your cluster expansion to it, and you'd get a bunch of pair interactions. So the first 6 are pair interactions. Again, blue, oh dear, change the color scheme here. Blue is the quantum mechanics now, the open circles are the potentials. And then there's some triplets interactions and some quadruplets interactions. And notice that the first pair interaction is negative. So what does that mean? That means the nearest neighbor spin product wants to be positive to get your energy down. So that means like things want to be together. Plus ones want to be with plus ones, minus ones want to be with minus ones, so that's phase separation. So you can already see it from the interaction. But notice the scale of the interaction. You know, so this is now about 40 milli-electron volt per cation. So this is a far cry. This is, you know, much lower than any direct electrostatic interaction or even any direct evaluation of a Buckingham potential, because you have effective interactions. Actually, if you think of the definition of the effective pair interaction, in this case, so let me write it out. So Vij would be 1/4. Let me actually put calcium and magnesium on here. So it would be E magnesium averaged plus E calcium minus 2 E calcium magnesium on the Ij sites. So you should think about where that interaction, that effective interaction comes from. Because look at the electrostatics. Does the electrostatics contribute? Magnesium and calcium are both 2+. Essentially, if you froze those two on their lattice sites, you'd have in the first term 2 plus 2 plus plus a 2 plus 2 plus minus 2 times a 2 plus 2 plus. So the electrostatics completely vanishes from the effective cluster interaction. So, you know, it's sort of interesting. The fact that you do this projection essentially filters out the largest part of the energy here in this system, but because it's the same for both magnesium and calcium and magnesium interactions, it's irrelevant for the configuration of thermodynamics, and the projection essentially filters that out. So where does the remaining Vij come from? Where does the balance come from? If you do a Buckingham, if you remember what we taught you in empirical potentials, the way you set up an empirical potential model for oxides is that you usually have, of course, the electrostatics. Then you usually have an oxygen potential, because the oxygen is the biggest ion they touch. And then you have a cation-oxygen potential. Rarely do you have a cation-cation potential. So there's not even a direct potential between the two. So if you actually froze these things on their lattice site, that Vij is 0. Because we just said that the electrostatics disappears. There is no direct cation-cation term. Okay? So Vij is 0 in the case. So I sort of gave the answer away. I said if you freeze these things on their lattice site, where does the interaction come from? Well, if you freeze them, there's no interaction. So all the interaction comes from relaxation. Okay. The interaction comes from the fact that calcium is bigger than magnesium. And so that sets up an effective interaction. So it's kind of cool because with these interactions, you have a Hamiltonian on a lattice model, which people always tend to associate with frozen positions. But the interaction comes essentially from the positions not being frozen. Okay? From the fact that, you know, the bigger atom pushes the smaller one away. Okay? And so this is maybe the key point to remember, that once you parameterize your Hamiltonian with relaxed calculations, that Ising model represents, okay, the energy of those relaxed configurations, not the ones where you're frozen at lattice sites. So when you do hydrogen on palladium, okay, you know, a lot of that interaction that you get between hydrogen on one spot on the surface and the other one has nothing to do with hydrogen-hydrogen interaction. It actually all has to do with relaxation of the surface sites around the hydrogen. You put a hydrogen here, the palladium around it relaxes. That's how it sees the other hydrogen. not because of a direct interaction. And that's, with hydrogen, that's not so dramatic. If you do that with other adsorbents like oxygen, it's very dramatic. Okay? They largely interact through a strain induced in the surface. Okay. So then you do Monte Carlo, and here's the phase diagram. It's a bit too many things on this slide, but essentially this is the line you should be looking at. This is the one with potentials. So these are the solubility limits at low temperature. So it's a two-phase region in between, but you have some solubility of MgO in CaO and of CaO in MgO. And this is the quantum mechanical one. So of course this becomes a miscibility gap because there's no liquid in the calculation. So if you somehow could include the free energy of the liquid, it would cut off that miscibility gap and form a eutectic. Okay? But because you don't have a liquid, you're essentially looking at only solid state transitions. And again, you see the same thing. The quantum mechanics gives you gives you a higher solubility limit, so lower temperature at which you can get full solution. Because it's in some sense easier, it can deal better with the lower symmetry state. Okay, so this is sort of the classic technique now to deal with any substitutional problem, and I would say almost any crystalline problem, because even if you work on systems where there are multiple lattice types in play. I mean, if you think of simple metals, you could think, well, maybe there's some that order on an BCC lattice and some that order on an FCC lattice. You can cluster expand them separately and obtain free energies from Monte Carlo and then put them together. That's why this is essentially the method by which any sort of multi-component crystalline problem is equilibrated. But I'll show you some of the older work just because historically it's kind of cool. This is the lithium aluminum system, which was I think only the second or third system that was done ab initio by this method. This was done in the early 80s. So the reason they did this in the early 80s because everybody thought we were going to make airplanes out of lithium aluminum because lithium is the lightest solid element in the periodic table. So any lithium you can put in an alloy makes it really considerably lighter. And the interesting piece occurs here, which you can't see. There's a delta phase here, which is metastable, sits about here. And what typically people do is they solution treat up a high temperature, then quench down so that you precipitate out delta phase to strengthen the alloy. It's difficult to do experimentally because this is a metastable phase, so it's a little hard to study it. But of course, computationally, all metastability means is that there's something else that's more stable. So as soon as you remove that from the picture in the simulation, you can stabilize it. And so this was one of those early calculations where they did exactly what we showed here. Build a cluster expansion, parameterize it with density functional theory. In this case, did Monte Carlo to do the statistical mechanics to find a temperature, and essentially get this calculated phase diagram. And there's the equilibrium phase diagram, but then you can also do the metastable. This is the delta phase precipitate by essentially removing the free energy curves of the stable phases and look at them. The liquid was kind of empirically added, I think, to this calculation. This was my own PhD thesis, so I have to show it. Most of my PhD thesis was just, 4 lines. So, I got off easily. But this is the phase diagram of yttrium barium copper oxide, which probably most of you are familiar is a fairly well-known high-temperature superconductor. And the critical issue, or one of the critical issues, was how the material behaves as a function of oxygen content. Essentially, that Z up in the formula can go anywhere from 6 to 7. And at 7, it's a high-temperature superconductor. At 6.5, it's a low-temperature superconductor. And at 6, it's an antiferromagnet. And so figuring out what the phase diagram looked like was, I guess, worth the PhD thesis. And essentially, it's again a lattice model problem. You have a bunch of sites where the oxygen can sit. When you start taking out the oxygen, it's now, the site can be vacant or filled with oxygen, so it's a binary problem. So you cluster expand it, same thing, you know. In those days, the quantum mechanics wasn't all that good, and you do Monte Carlo and you get a phase diagram. And what's neat about this O2, to my knowledge, this phase, I think there's sort of just some history with it, was probably the first structure, I think, that ever was predicted with quantum mechanics before it was seen experimentally. Now there have been a lot of cases of that, but this goes back to, was actually in the late 80s. And it may have been the first case where the experimental evidence came afterwards. Okay. Here's a lot more complicated system. So, you know, this is the lithium cobalt oxide I showed you in the beginning. There's, you know, cobalt layers, there's oxygen layers, but the key component is the lithium layer. As you take lithium out, you have a vacancy lithium problem. So again, you expand in variables that only describe the occupation on this layer. Okay. So you don't really have to deal with the cobalt, with the oxygen. You just deal with that when you do the energy calculations. And you get a bunch of effective interactions. And again, let me stress that these ECI are effective interactions. If you look at the first neighbor, it's only 30 millielectron volt. Okay? You know, to give you an idea, those first neighbor distances in the lithium plane are about 3 angstrom. If you evaluated the electrostatics of a +1 charge and a +1 charge over 3 angstrom, you'd get something that's close to an electron volt. Okay? But you see, because you're taking effective interactions, you essentially remove most of that. Well, first, some of it is screened because, you know, you're not in a vacuum doing your electrostatics. Some of it is screened by the oxygens that are close by. But you're also canceling a lot of energetic effects and really seeing the only part that's relevant for the thermodynamics. Then you can, again, do Monte Carlo just like we've done in the lab, get a phase diagram. This is the kind of phase diagram that you would not get out of straight Monte Carlo. The hydrogen on palladium problem we gave you, you can do that literally by looking at the output of the Monte Carlo, by looking at the heat capacity, looking at the energy, because the system equilibrates very well. When it doesn't equilibrate, you really have to do free energy integrations and look at where they intersect. And so this phase also was predicted 3 years before it was seen experimentally. So this approach has really very powerful predictive capability because you control almost all the approximations. So essentially, you know, you have to live with the approximations in density functional theory. You know, so whatever the accuracy of your electronic Hamiltonian, you can't do any better. Okay? But from there, you control all the approximations. So if you don't like the convergence of your cluster expansion, well, you know, you add more terms to it. Okay? So essentially, you can make as accurate a representation of your quantum mechanics as you want. And that's why you can make Hamiltonians that are very accurate, but they live on a lattice model, so they're extremely fast to search. I mean, you've done the hydrogen on palladium. Hydrogen on palladium does, you know, that trivial Java code does 4 or 5 million spin flips per second on a stupid old IBM computer. So on a new machine, you can run 10, 15 million spin flips per second. So you can search configuration space extremely fast. Okay? And so that's why it's so good at finding new structures. Okay, I was going to show you a surface problem. So here's platinum 111. Reason I took platinum, it's sort of an important material for all kinds of catalysts and so. And every time you have these FCC surfaces, the possible adsorption sites essentially form a triangular lattice. I should go to a different color here. So you have these really all form a triangular lattice. There we go, triangular lattice. So if you want to study the adsorption of something like hydrogen or oxygen, again, you build a lattice model. Then you have to do density functional theory calculations to parameterize it, and I think you've done that now in the lab. So because this is a surface, you would set up a slab geometry. So you essentially would take a few layers of platinum and then put stuff on the surface to adsorb it. And you put a set of vacuum a range of vacuum above that and do the DFT calculations. Okay, so here's that result again. This shows both LDA and GGA, but again we plot them. This is oxygen absorbed on platinum 111. We reference the full coverage and the zero coverage to 0. You may be a little surprised that you can set 2 points to 0 on the energy scale. Well, one of course is obvious, so you can always reference 1 point to 0 on energy scale. The reason you can set the second one to 0, what you're essentially doing is setting a 0 for the chemical potential. Because the chemical potential is, in some sense, the slope of that curve. Okay? It's the energy change just by adding oxygen in this case. So you're essentially referencing the chemical potential to 0 by setting 2 points to 0. So you do that. Same thing, you fit interactions. You know, I've shown here, I've actually made some copies of real notes so you see how this is really done. So people sketching out on a triangular lattice different interactions. You find their value. Again, they're very small. The black points is for oxygen on platinum. The L1 is on ruthenium. You know, this is about 75 for a near neighbor interaction. And then it decays very quickly, very fast. And you know that they actually have to be in that range because if you're going to see phase transitions in the range of, say, 0 to 1,000 Kelvin, your energies have to live on that energy scale. And, you know, 1,000 Kelvin is what, about 100, well, 1,000 Celsius is about 100 millielectron volt. So your interactions have to kind of be in that range if there's for stuff to happen. So I thought I'd show you, rather than a nice picture of a phase thing, hold on. So how would you look for phase transitions? You do the same stuff you do in the lab. You track heat capacities, you track energies. So this is for the same run, different oxygen chemical potentials. So with your experience, what's happening here at about 940 K? This clearly looks like a phase transition, first or second order. What's your guess? Second? It's hard to say, but it looks like second order. I mean, you know, it's maybe not refined enough to look, but there's clearly a peak in the heat capacity. Like, let's say we take, I don't know, the green curve, you know, which is at the particular oxygen chemical. There's a peak in the heat capacity. It's not very well defined, you know. You shouldn't let yourself mislead. You know, that if you didn't draw the lines here, but just the points, that peak is essentially defined by 1 point. Green. So you should always be careful, you know, you may have very spurious behavior going on in one similar Monte Carlo situation. The other peaks have slightly more points, but normally if you really wanted to know whether it's first or second order, you would refine it a lot more near the phase transition. Again, the energy seems to be continuous, but don't let the lines fool you. Huh? You've taken, like, say, this point and that point and connected them, so of course they're continuous. But, you know, maybe what this thing does is it kind of continues and then shoots down to that other vertically, so it could still be first order. So you would normally refine this a lot more. And the other thing, if you really want to know that something's second order, you look at the scaling of the heat capacity with system size, and that's the really accurate way to know that something's second order. Your normalized heat capacity in a second order transition, so the heat capacity per site scales like the square root of the number of lattice sites. You'll find that already in your simple example, your simple homework problem of hydrogen on palladium, you'll find it remarkably hard to identify in certain regions where their phase transitions are first or second order. That's why you put them in. There are both first and second order. So rather than a beautiful phasing, I thought I'd show you guys how it's really done. You know, when we do Monte Carlo, this is sort of, it's really like a puzzle, you know. In papers, we always show these nicely drawn things, but this is how you get to it. You do an enormous amount of scans in mu, so you scan this way, then you scan in temperature, and you slowly start piecing together, you know, which phases exist where they disappear, how they disappear, first or second order reaction. So this is like one that is near completion with a few sort of question marks, whether these are like first or second order. And then later you draw like nice lines, but But it really, this is one of the problems with Monte Carlo because it's a stochastic method. It really is a lot of puzzling. And what you'll find is that the last thing that's useful, the least useful thing, is actually looking at the spins. That's people's first intuition. I'm going to actually look at the configuration in my system. You know, anytime systems are sort of partially disordered, just looking at them is like the best way to fool you. If you look at something partially disordered, half of the class will say it's ordered and half of the class will say it's disordered. And it's really the thermodynamic behavior that tells you in which phase it still is. If it's in an ordered state, so in a compound state, that means that you should be able to push it to a disordered state. Okay, that means you should see somewhere a phase transition as you raise the temperature or drive the chemical potential to another phase. If it's already disordered, if you heat it further up, it won't go to a phase transition anymore. Okay. Just to show you that you can push this a lot harder and make it a lot more complicated, I'll show you something that gets a little more abstract. And it's sort of from a problem that I worked on quite recently. It's adsorption-induced segregation, and here's the problem. So the problem before was oxygen adsorbent on platinum. But if you have actually a platinum metal alloy, like platinum metal catalyst, in this case platinum ruthenium, then you have two configurational problems. So the first question is, what's on the surface? Is it oxygen or vacancy? Is the side oxygen or vacancy? But there's also a segregation thermodynamics now. On the surface, you now may not have pure platinum. You may have either platinum or ruthenium. Okay? And the two interact. What segregates to the surface is influenced by what adsorbs. You see, that's actually, you may think of that as a quaternary problem, because essentially what's in play now, platinum is in play, ruthenium is in play, oxygen is in play, and vacancies are in play. Vacancies being vacant adsorption sites. But it's actually a 2 + 2 problem. It's really a binary configuration problem in the surface layer, and then a binary configuration problem on top of the surface layer. And so you can still perfectly solve this with a binary cluster expansion. It's just that your spin means something different when you're in the surface layer or when you're in the adsorbent layer. So you could call them different, but you don't have to. You could say, well, there are variables that is, say, whatever. This describes what's in the adsorbent layer, and I could just call a new set of variables delta. This describes what's in the surface layer. Okay? And then I could literally expand in the products of these. But to be honest, you could just all call them sigmas. Huh? Okay. They just mean something different, whether they're defined on this side or on that side. Okay. And so you can do the same technique and now essentially expand a quaternary problem. And you know, you do the same whole thing, you calculate a lot of configurations. Because your configuration space is essentially bigger, you'll need more information to parameterize it. And then, you know, you do Monte Carlo and you equilibrate it, and here's an example. This is at a given temperature driving up the oxygen chemical potential, so you expect more oxygen to adsorb, and that's what you see. But you can actually track the amount of ruthenium segregating to the surface, and as you bring more oxygen to the surface, you actually start increasing the amount of ruthenium in the surface as well. And so you can, you know, you can really solve the thermodynamics of these problems by ab initio methods, by going through this cluster expansion approach. You can actually look at the sites. Orange is the platinum surface, red is the oxygen adsorbed, and this picture here is the same with the oxygen stripped off, so you see underlying ruthenium. So as you increase the oxidation, you essentially get more ruthenium to the surface and more oxidation. This is sort of more and more higher and higher oxygen pressure. So, okay. Let me show you one more quickly before I continue the theory. And the reason I want to show you this is because it's sort of a little different. This is a structural problem from hydrogen-modified aluminum fracture. Okay. The problem there is that impurity embrittlement in metals is a big issue. There's a lot of metals that whose ductile behavior becomes very poor when there's impurity present. And hydrogen embrittlement in particular is a bad one. And it's not that hydrogen is so much worse than other impurities, but first of all, hydrogen tends to be a common impurity because it's available everywhere. Anytime you have corrosion reactions going on, you often produce hydrogen. Anytime you're working in acid environments, you produce hydrogen, and it tends to be a fast diffuser. So there's a lot of other impurities, but a lot of other impurities sort of never make it to the problem areas in the material. But hydrogen tends to be a fast diffuser. So the way people have dealt with this in quantum mechanics is literally by looking at how planes decohere with and without hydrogen. And of course, if you put hydrogen in between it, it decoheres more easily. There's less work of decohesion. But if you want to look at the structural problem of what happens when you do this with hydrogen, if you want to equilibrate the hydrogen, it becomes a lot harder. So let me sort of first tell you, how would you do this without hydrogen? You could make a slab. You would sort of, define a plane where you open up the slab and you pull, you remove the two slabs farther and farther apart. So it's like you're opening a crack. You keep track of the energy, and the derivative of that is, of course, the force required to separate the slab. But think of the problem now if you want to do that with an impurity. You have to now equilibrate the impurity at every separation of the slab. Okay? So, you sort of, pull the crack open a little more. You now have to figure out what happens to that impurity there. Because as that impurity equilibrates, okay, not only its structure, it equilibrates, by the way, but also its composition, because segregation to those surfaces is an open system problem. Okay? The concentration there is not fixed because it comes from the bulk or from a gas phase. So it's actually a grand canonical problem. It's a constant chemical potential problem rather than a constant composition problem. So you see that the hard problem you have, not only do you have to arrange the impurities in the most stable way, because that's going to determine the energy and therefore the force it requires to open up those planes, but you also need to equilibrate the amount of impurity in that crack. And so this is actually why it's so hard to include chemistry in mechanical calculations, because you're really working on two different time scales that are very hard to combine. And so the solution here was essentially to calculate the relevant free energy of hydrogen for any state of crack opening. Okay. For any state of separation of the planes, you try to get the equilibrium hydrogen content by a cluster expansion. And then from that envelope of free energies, you get the force. So it's, again, the same thing. You define a lattice model for, this was hydrogen on one side of the crack opening, hydrogen sites on another side of the crack opening. So now you have interactions within one plane, but also between the two. You do a bunch of first principles computations. So it's, again, the same thing. To fit those interactions, then you're going to do Monte Carlo. You're going to, in this case, get your free energies, and the derivatives of the free energy with respect to the separation is going to be the force. So in this case, this is the force as a function of slab separation for all the different hydrogen coverages. So I plotted the force. I really should have plotted the energy, because it's the energy is the quantity that's expanded. And then you get interactions. In this case, I'm only showing two. So there's an in-plane hydrogen interaction. That's the red one here. And there's an interplane. The interplane is between the two openings of the crack. And of course, that one tends to go to zero as you separate more and more. Okay? So now, the cool thing is, at every state of the crack opening, you can actually get the free energy of the system fully equilibrated. And so if you get the free energy, you can actually find the force. And this is the fully equilibrated thermodynamic trajectory, that red line. And what's really surprising is that because you fully equilibrate the system, it suddenly looks very different from what you thought it would be and what you would have gotten in an unequilibrated calculation. These black lines, this is what you got in an unequilibrated calculation. It sort of makes sense, As you pull, the force goes up, no surprise, and then you reach a critical point, point of maximum force. At that point, you're unstable because essentially the force as you pull further goes down, so you're unstable. On the downslope, you're essentially unstable. But look at the red line. So this is a chemically equilibrated system, behaves very different. Essentially, you pull a little bit, okay, you open the crack a little bit, and then the crack opens with no increase in force. Okay? And then you pull the saturated crack apart. And essentially what this is because you've done your thermodynamics right, you actually have a first order transition in length space. Okay? This is, this is just like this is a length discontinuity. It's just like a volume discontinuity in a regular first order transition. Okay? Here essentially the crack is separating at constant force. Okay? It's like if you it's like when you do a first order transition upon heating, you're putting in enthalpy at constant temperature, for example. Or if you do a pressure-induced phase transition, you get a volume change at constant pressure. Okay? So it's the same thing. But you see that by doing the chemistry right and the equilibration, you get very different results. Okay. So the last thing I want to do is sort of come back to the idea that we started with. And I wrote down the energy as a function of configuration and then showed you how you cluster expand it. What I want to do is now come back again to what the definition should be of that energy. And we sort of did that at the back end of the Monte Carlo lecture. But because it's kind of important, I want to come back to it. Because it's not totally clear what that energy or that Hamiltonian in the lattice model should be. So let me take a step back, and I know you've seen this, but I want to go through it. If you want to get the free energy of a system, you normally want to include all excitations. Okay? Because essentially you have to calculate the partition function. You have to trace over all excitations, and that will give you the full partition function, and the logarithm will give you the free energy. So if you think of the most basic system, we'll always have vibrational excitations. Okay? If we have anything with a binary problem, like A's or B's or something and vacancies, we'll have configurational excitations. And then, unless you're in an insulator, you'll have electronic excitations. The idea we talked about last time is that the way you can define a Hamiltonian that lives in this space, which is the one with the slower time scale, is by integrating over the faster time scale. And I started to show that you last time, I think, when we finished the Monte Carlo lecture. And let me sort of go through that sort of formal description again so we see exactly what our lattice model Hamiltonian is. So I'm going to do it here only with vibrations as the fast time scale and substitutions as the slow time scale. And after that, you'll see how it would go with electronic excitations as well. So I replace the coordinate Ri, so this is a set of coordinates that describe the atom, into a lattice site position and a deviation from that lattice site. Okay. The lattice site position, that is fully defined by the set of configurational variable sigma. And the deviation from the ideal lattice site position I'll call the configuration nu. So the combination of sigma and nu is really the same as the set of vectors Ri. Okay? So what I'm going to do is you always see where I'm going probably with this. I'm going to trace over the nus to get a Hamiltonian in the sigmas. Okay. So the full partition function is the sum of the exponential of the energy, which depends both on sigma and nu, and I sum over the sigma states and the nu states. Okay? What I'm going to do is I'm going to do the inner sum, so that I'm only left with a sum over sigmas, okay, of some f, which is the Hamiltonian in the configurational space. And if you look to make these two the same, what that f should be, well, f is the free energy that I get by tracing over the news. Okay? I mean, there's no physics here. Huh? This is pure and simple substitution of variables. So I call essentially this sum here is the exponential of minus beta f. Okay, which means that f is the log of that exponential. So, but look at what I sort of formally end up with. I have a partition function that only sums over substitutional states. So this is a problem that lives in the same space as a lattice model, okay? Because I'm only summing over discrete configurational states. So what I'm really saying is that if I do this partition function correctly, I have the full partition function and therefore the free energy. But to do it correctly, my Hamiltonian in my lattice model state needs to be f, not E. And what is that f? Well, f is essentially a free energy. Huh? It's the log of a partition function. And what partition function is it? It's the partition function by summing over all the faster states. So the problem is essentially simple. Huh? The Hamiltonian you should use in your slow time scale space is the one you get by integrating or by calculating the free energy of your fast time scales. So in this case, what should you do? In everything I showed you earlier this morning, I used the energy as the Hamiltonian. Okay, I used the direct DFT energy in my Hamiltonian. What I really should have used is the vibrational free energy to be correct. If I used the vibrational free energy in that Hamiltonian, I would have gotten the full partition function, and therefore I would have gotten the total free energy of the system. So what did I do instead? I didn't calculate this. I approximated this by something. You know, I approximated this by the state in this ensemble with the lowest energy. I mean, if you think of this as a free energy, this is going to be a free energy plus some entropy plus an entropy term, which you could think of as a ground state energy plus contributions from excited states. Okay? I've basically said I'm taking this just as the ground state energy in this ensemble. Okay? Because I'm taking the lowest energy configuration that I can get by varying over this. Okay? And what is varying over this? What are the news? The news are the displacements from the lattice sites. So essentially, I'm relaxing my system, letting it displace from the lattice sites. I get the lowest energy state in the ensemble, and that's what I expand. So when I'm done, what do I have? When I'm done and I do Monte Carlo with that Hamiltonian, you know, I have essentially the right energetics. I have configurational entropy, but I don't have vibrational entropy. To have vibrational entropy, I would have to do this sum, not just take the lowest energy term. Okay. Come on. Okay, let me sort of skip that. Okay. People actually have done examples where they do the full integration over vibrational states rather than just approximating that ensemble with its lowest energy term. You see that it's a lot more work. Remember that to parameterize the cluster expansion, I need the Hamiltonian evaluated for a bunch of configurations. Even in the simplest case, that's easily 40, 50 configurations. So if you want to include the vibrations, you actually have to do, for 50 configurations, the full phonon DOS, and or do molecular dynamics on them and integrate the phonon and get the vibrational free energy through that. So it's like 2 orders of magnitude more work. So rather than just the energy, you want to get the whole vibrational spectrum. And that's why people usually don't do it. But the nice thing is that in this approach, you can do it if you really want to. But I'll show you one example where people did it and looked at the difference. It was the very simple case of the cadmium-magnesium phase diagram. It was done by Mark Asta, who's now at Northwestern. So this is the experimental phase diagram, actually. So this is the calculation with no vibrational entropy and with vibrational entropy. So the first one is the one that I sort of showed you as the standard one. You just take the lowest energy for a lattice model configuration and you do Monte Carlo then with that. And this is if you literally do the whole phonon dust for every configuration. And what you see is that, you know, there is some change in topology. I mean, look, at this point has come down considerably and even has changed the topology somewhat. And usually that's what you'll see. You rarely see new phases, new ground states come in when you include vibrations. But you will change the topology of phase diagrams, for example. There are a few known cases, you know, usually people write a physical review letter whenever they find one where phases come in purely stabilized by their vibrational entropy. It's a bit of a puzzle, actually, why it doesn't happen more, because the vibrational entropy is large. It's essentially, you know, 3R. Remember the law of Dulong-Petit? It's, you know, the entropy is 3RT. The heat capacity is 3R, so the entropy is 3RT. The configurational entropy at its maximum is only R log 2. You know, at 50-50 in a binary reality, you have the maximum entropy, and that's only, it's actually the logarithm of 1/2. So it's minus the logarithm of 2. So you either have, that's about what, 0.67. So the configuration entropy is only about 0.67 R. The vibration one is 3R. So it's a lot bigger. But of course, what matters is the difference in that quantity between different structures and different states. And even though the configurational entropy is the smaller one, it tends to be the one that's more different between different states than the vibrational one. And that's why we sort of all hope that it's okay to often leave the vibrational entropy out, because it often, most of it tends to cancel between different states. Okay, so sometime in 1994, somebody compiled all the systems done with these methods. This was 1994. We stopped compiling after 94 because there were just way too many studies going on. But this kind of approach has now been used to study hundreds and hundreds of sort of ab initio structure and thermodynamics problems. People do higher component now, ternaries. It's still a lot more work. This is a simple ternary. And then I gave you a series of references. I wanted to show you some of the older work. That's actually the last references here. You know, often the older work, even though it's not up to date, but it's also not confused by a lot of complications, so it's often very easy to read, very elegant to read. But the key review paper is essentially this one, which is like 150 pages or something like that, which contains the ideas of the cluster expansion and a lot more. And then my own work is, this is a short review on how that works, how you apply that in oxides. And the one by Alex Zunger is essentially the same thing, but how you apply that in semiconductors. And the fourth one is kind of the most recent one, which my own graduate student wrote, Axel van der Walle, because he's been kind of instrumental. You know, he's gone to making this into automated codes and so on, has a whole code suite, and the paper is about that, how you train Monte Carlo and so to automatically look for phase transitions and things like that. Okay, I think that's it. So let's see, what day is today? Today's Thursday, so Tuesday we'll meet again here. I'll start talking about accelerated molecular dynamics and find another topic to talk about as well. So, and then Thursday is Chris Wolverton. So I'll see you. Have a good weekend.